Okay, so now I'm going to be teaching you how to do calculations involving pH. You learned about the pH scale and the pOH and what hydronium is in the videos from Bozeman and Crash Course. So now I'm going to just briefly explain pH, what it means, and then get into some calculations. So the pH scale, it goes from 0 to 14, okay? The lower the pH, the more acidic something is. The higher the pH, the more basic it is. Water is pH 7. So it's obviously neutral, which is good. Okay, a change in 1 on the pH scale actually represents a 10-fold increase in concentration of acidity, increase of hydronium concentration. And that's because it's a logarithmic scale, a 10-based scale, okay? So if something has a pH of 2, it's 10 times as acidic as something with a pH of 3, for example. Okay, so if you want to take the pH of something, and you're given the H plus concentration, which, by the way, you can say in any calculation, H3O plus basically means the same thing as H plus for our purposes in this class. Okay, you'll learn something slightly different in AP chemistry, but for our purposes, just assume that. Okay, so the pH of something is equal to the negative log of the H plus concentration. So in your calculators, you're going to do negative sign, okay, and the log button, okay, not inverse log. Inverse log is something we're going to do separately, okay. Negative, the log button, okay. And if you're using your cell phone, if you're using a cell phone, you might have a 10 to the X button, and in that case, you would have to do the inverse. And if you're needing help on how to figure out how to use your particular calculator to get the log of a number, just look it up on Google, on YouTube, okay? So the negative log, the pH of a solution, that's 3.4 times 10 to the negative 5th molar. A little trick here. Something that has an exponent of 10 to the negative 5 should have a pH around 5 because it is a logarithmic scale. Same thing here. H plus solution is negative 4. And if we put negative log 6.7 times 10 to the negative 4 into our calculators, we get a pH of 3.2. And for simplicity's sake, just round it to the same number of decimals that you had. So when you put an acid in water, the acid is separated by the polar water molecule. So it's going to pull apart the ions. So it's going to pull the hydrogens away from the chlorines if you've got something like hydrochloric acid. Okay. So we can use the concentration of our acids to help us figure out how basic or acidic our solutions are. Okay. So there are several different types of acids, and it depends on how many hydrogens are present to balance off the anion. Okay, so something that is monoprotic, okay, I'm sure you guys can figure this out, but something called that's monoprotic has one ionizable hydrogen. Okay, so if your concentration of hydrochloric acid is 1.5 times 10 to the negative 2, then it will be the same, the H plus concentration is going to be the same as that because it's a strong acid. 1.5 times 10 to the negative 2 molar. Okay. If you have a diprotic acid, such as sulfuric acid, okay, if sulfuric acid, if you take a look at it, so I'm just going to draw it here in my amazing drawing style. Okay, I have an SO4 with a -2. That's what sulfuric acid looks like. So when you dissolve sulfuric acid in water, it's actually going to have twice as much acidity because for every 1 mole of this, so if you have one, let's say you have 1 mole, a 1 molar solution of sulfuric acid, okay, when it breaks apart in water, you're going to have 2 molar of H plus, because you're going to get twice as many H's for the number of sulfuric acids that you have. So since there's 2 H's, if you have a 1.5 molar, 1.5 times 10 to the negative 2 molar solution of sulfuric acid, you get twice as much. So the concentration of H plus is not equal like it was in hydrochloric acid. It will be actually twice as much. Monoprotic, diprotic. What do you think's coming next? Triprotic for the win. Okay, so things like phosphoric acid. Phosphoric acid has 3 ionizable hydrogens. So you're going to get, let's see, H plus, H plus, H plus, and then you got your phosphate group. Okay, so when this is all together and you say this is 1.5 molar, 1.5 times 10 to the negative 2 molar, we'll say that. Well, when it breaks apart in water, you're going to have 3 times that amount. 3 times 1.5 times 10 to the negative 2 molar. Okay, so it's going to be 4.5 times 10 to the negative 2 molar. Okay, so we're going to assume that all the acids we're working with are strong acids. And what that means is that all of the hydrogens break apart from their anions. Okay. So if we have a 1.0 times 10 to the negative 2 solution of hydrochloric acid, the pH of something is equal to the negative log of the H plus concentration. Okay. So, and guys, look at this. My base is 1. So I really don't necessarily need to put this in the calculator, but I'm going to do it for fun because I like to have a lot of fun around here. Okay. My answer is going to be negative log of 1.0 times 10 to the negative 2 molar. So that's going to give me 2.0. And pH doesn't have a unit. Okay. Doesn't have a unit at the end. It's just the pH. Okay, so the molarity kind of disappears. So if we have 3.25 times 10 to the negative 2 molar hydrochloric acid, pH equals negative log of my H plus concentration. And since this is a monoprotic acid, my H plus concentration is going to be the same as my concentration of my acid, because there's just one H. Okay, so negative log of 3.25 times 10 to the negative 2. Okay, I'm going to put that in the calculator. Whoops. Okay, and I'm going to give it the same number of digits, and I'm going to get that to be 1.49er. Okay, so slightly more acidic. Okay, which makes sense because remember the number is lower, which means it's going to be more acidic. And it's like 3¼ times more concentrated. Okay, so what is the pH of a 1.5 times 10 to the negative 6 molar sulfuric acid solution? Now, we have to remember that this is diprotic. Okay, so that means my H plus concentration is going to be equal to 2 times 1.5 times 10 to the negative 6 molar, okay, which is going to give me 3.0 times 10 to the negative 6 molar, okay. So it's my H plus. And I'm not going to worry about this affecting my significant figures because it's a 2. It's just 2. It's not going to affect your sig figs. So your H plus is going, your pH is going to be the negative log of that H plus concentration. Okay, so negative log of 3.0 times 10 to the negative 6 molar. Okay, and that is going to get you a pH of 5.5. Okay, so it's still acidic, but not very acidic, because my my exponent is 10 to the negative 6. All right, let's try this one. We've got phosphoric acid, which is triprotic. Okay, so my H plus concentration is going to be equal to 3 times 2.06 times 10 to the negative 4 molar. So that's going to give me 6.18 times 10 to the negative 4 molar. So my pH is the negative log of 6.18 times 10 to the negative 4 molar, which gives me a pH of 3.21. I can go the other way. What? Yep, that's true. So since the pH is the negative log of the H plus or hydronium concentration, you can solve for the H plus concentration. And therefore, you can then also solve for the concentration of your original acid. Okay. So if we have hydrochloric acid, so you really need to be paying attention to whether or not the acid you're talking about is mono, di, or triprotic. Okay. So we've got HCl with a pH of 5.0. Okay, so H plus concentration is going to be equal to 10 raised to the negative 5.0, which is, not even going to put this in the calculator, not going to dignify that, okay? 1.0 times 10 to the negative 5 molar. Okay? So make sure that this negative sign goes there. Otherwise, you're going to have a really bad time. All right? Fabulous. Next question. Hydrochloric acid with a pH of 1.8. So my H plus concentration, which is the same as my HCl concentration, is 10 raised to the negative 1.8, which my calculator tells me is 0.016 molar. And if you're feeling very fancy, you could write this in scientific notation. You could write this as 1.6 times 10 to the negative 2 molar. Oh, looky here. My acid here in this next problem is sulfuric acid, which is diprotic. Okay, so that means, if we think about what my H plus concentration means in terms of the concentration of my acid, my H plus concentration is equal to 2 times the concentration of my acid. Okay, so when I solve and get my H plus concentration, I have to make sure that when I want the molarity of my sulfuric acid, my original solution, I divide it in half, because the fact that there are 2 H's here bumped this up by 2 times. So let's do that calculation. Okay, so pH, so hold on a second, H plus is equal to 10 to the negative 5.0, okay, which gives me 1.0 times 10 to the negative 5 molar. But remember, that's just my hydrogen concentration. My sulfuric acid concentration is half of that, because I got twice as much bang for my buck. For each H2SO4 that I put in, I got twice the amount of H's. So I'm actually going to take that and divide her by 2. Okay, so then I'm going to get 5.0 times 10 to the negative 6 molar. That's the concentration of H2SO4. Okay, let's just do a few more. So we're going to be dealing with the same numbers just for simplicity's sake. So we have sulfuric acid with a pH of 1.8. So we have already solved this, the H plus concentration of this up here. So my the H plus concentration here was 1.6 times 10 to the negative 2 molar. But remember, because this is a diprotic acid, I need to divide this by 2 to get my H2SO4 concentration. Okay, and that gets me 8 times 10, or 8.0 burger, times 10 to the negative 3, okay, molar. That's my sulfuric acid H2SO4 concentration. Okay, it gets tricky when you have these mono, di, and triprotic acids. Okay, so now we're going to go to a triprotic acid. And we already did this calculation before, again, that the H plus concentration of anything with a pH of 5 is 1.0 times 10 to the negative 5 molar. But because this is a triprotic acid, we're going to divide this by 3 to get our concentration of H3PO4. Okay? And that's going to get me 3.3 times 10 to the negative 6 molar. Okay? All right. And now we have this pH 1.8 again. So the pH, anything with a pH of 1.8, we see up here, it's 1.6. So the H plus concentration is 1.6 times 10 to the negative 2 molar. And because this is phosphoric acid, we need to divide this by 3 to get the concentration of the acid itself. So it would be 0.053 molar H3PO4. Okay, so if you have a base and you take the inverse log of its concentration, you're not actually getting its pH, you're getting its pOH. Okay, it is the lesser used calculation, but it's useful if you're trying to solve for concentration of base. Okay, so similarly to acids, bases can be monobasic, dibasic, and tribasic. And if you think we're going to go through this very similarly to the way we did it before, you are exactly right, student. Okay, so if you have like potassium hydroxide, which is a monobasic base, you get 1. So for the concentration of KOH is equal to the concentration of OH minus. Okay. So similarly, again, if you have like calcium hydroxide, this is going to double the concentration of your hydroxide if you have the same molarity of calcium hydroxide. So let's say if your calcium hydroxide concentration is 4.0 times 10 to the negative 3, the hydroxide concentration, the OH minus concentration, will be equal to 2 times 4.0 times 10 to the negative 3. It's a good thing I'm writing this all out because 2 times 4 is 8, equals 8.0 times 10 to the negative 3 molar. Okay, and then if you've got a tri-basic base like aluminum hydroxide, that will be 3 times as much. Okay, so, and this should say pOH. Okay, what is the pOH of a 1.0 times 10 to the negative 2 molar lithium hydroxide solution. Okay, so our POH, it's going to be the same. It's going to be POH is equal to the negative log of the OH minus concentration. Okay, and since lithium hydroxide is a monobasic base, the concentration of the hydroxide is going to be exactly the same as the concentration of your base. So our POH is going to be negative log of 1.0 times 10 to the negative 2 molar. Okay, and that's going to give you 2.0. That's your POH though. Okay, that's not your pH, because if you're looking at that number, you're like, man, that looks like an acid to me. So one thing I want to point out to you is if you take your pH plus your POH, you get 14, always. Okay, so if you want to talk about this in terms of pH, you would just say, all right, well, then my pH equals 14.0 minus 2.0, which is 8.0. Okey-dokes. Cool. All right. So, similarly here, we've got lithium hydroxide again, monobasic base. So we have a 3.25 times 10 to the negative 2 molar basic solution. Negative log of 3.25 times 10 to the negative 2 molar. That gives me my POH. That's a really ugly looking P, but I'm going to leave it. Okay. And that gets me 1.49. That's my POH. Okay, so if I want my pH of this, pH equals 14 minus POH. So that'd be 12.51. And just give it as many digits, decimal places, as what you had there. Okay. Ooh, calcium hydroxide. That's a dibasic base. That's exciting. Okay. So our hydroxide concentration here is going to be 2 times the concentration of our calcium hydroxide. Okay, because we have 2 hydroxides for every calcium hydroxide. So our hydroxide concentration is going to be equal to 2 times 1.5 times 10 to the negative 6 molar. So that gets me 3.0 times 10 to the negative 6 molar hydroxide. Burger, read it correctly. Thank you. Okay, so then now my POH would be the negative log of that. Okay, and that gets me 5.6. Okay, that's my POH. Okay, which is what you were asked for. Again, this should say POH. So if you wanted the pH, it would be 14 minus 5.6, which gets me 8.4. Coolio. Oh, look at this. We've got a tribasic base. Okay, and it's all about that base according to Megan Trainor, right? Okay. Well, yeah, I had to, right? Okay. So, because this is tribasic, my base concentration, my hydroxide concentration, is going to be equal to 3 times 2.06 times 10 to the negative 4 molar. Okay. And that's going to get me 6.18 times 10 to the negative 4 molar. That's my hydroxide concentration. Okay. And so to get the POH, I'm going to do the negative log 6.18 times 10 to the negative 4 molar. Okay, which gets me 10.79. Oh, that's my, sorry, moving ahead of myself. That gets me 3.21 as my pOH. So my pH is 14 minus 3.21. Okay, and that gets me 10.79. Okay. So we already did this, solving for the pH of all the previous problems. People just don't use pOH. So it's not commonly used. pH is used more. So you just do 14 minus the pOH gives you the pH. Okay, so if you want to go the other way, if you have a pH and you know what kind of solution you have, you can solve for the concentration just like we did with the acids. Okay. But you have to pay attention to whether or not it's mono, di, or triprotic. So if you have sodium hydroxide with a pH of 8, okay, sodium hydroxide is a monobasic base. So my OH minus concentration is going to be equal to my NaOH concentration. Okay, and that's going to be equal to 10 raised to the negative 8.0. Oh, you know what I did? I made a mistake, Mrs. Berger, because I gave a pH here, not a pOH. Okay. So that means my pOH, if it's 8.0, my pOH is 6.0. Okay. So it's going to be 10 raised to the negative 6.0. So my concentration is going to be 1.0 times 10 to the negative 6 molar. Okay, now I've got sodium hydroxide with a pH of 11.8. Well, my pOH is going to be 14 minus 11.8, which is 2.2. Okay, so then I'm going to do OH minus is equal to 10 to the negative 2.2, which is 0.006 molar. I could put another digit there. So it's 6.0 times 10 to the negative 123 molar. And since this was monobasic, that's the concentration of sodium hydroxide as well. All right, so then now let's take a look at this dibasic base. Okay, my pH is 8.0, so similarly to up here, my pOH is equal to 6.0. Okay, but when we go to get our concentration of our solution, our original solution, our OH minus concentration that we're going to get, we're actually going to have divide it by 2 to get the concentration of magnesium hydroxide. Because for every 1 magnesium hydroxide, we got 2 hydroxides from it. Okay, so let's solve this. So we're going to do 10 raised to the negative 6.0 equals my OH minus concentration. Okay, so it's going to be 1.0 times 10 to the negative 6 molar. That's my hydroxide concentration. My magnesium hydroxide concentration is going to be that divided by 2. Okay, so it's going to be 5.0 times 10 to the negative 7 molar. Okay, so let's take another look. So here we've got magnesium hydroxide with a pH of 11.8. And you can see from up here on this slide that we already know here that the pOH is 2.2. And when we get our OH minus concentration, it solves out to be 0.00060 molar. But because this is dibasic, I need to divide this by 2 to get my magnesium hydroxide concentration equals, so this will be 0.0030 molar. Okay, so what if we've got boron trihydroxide? Okay, so that's a tri-basic base. Okay, so if we have a tri-basic base, whatever our hydroxide concentration is that we're solving for, we're going to have to divide it by 3 to get our base concentration. Okay, so let's do this one from the beginning. Okay, so if we've got a pH of 8.0, that means my pOH is 6.0. Okay, my OH minus then, okay, my OH minus is equal to 10 raised to the negative 6.0, okay, which gives me 10 raised to the negative 6.0, which is 1.0. I don't know why I struggled with that. 1.0 times 10 to the negative 6 molar. Okay, so this again is 3 times as concentrated as our original solution. We're getting 3 hydroxides for every boron trihydroxide. Okay, so I'm going to have to take this molarity and divide her by 3. Okay, and that's going to get me 3.3 times 10 to the negative 7 molar. Okay. If we've got BOH3 with a pH of 11.8, okay, so pH of 11.8 gives us a pOH of 2.2. All right, with a pOH of 2.2, our OH minus is going to be, it's the same as up here, 0.0060. And since it's boron trihydroxide, we then have to divide this by 3. Divided by 3 gets us the concentration of BOH3. Okay, which would be 0.0020 molar. Okay, so we can also use, to help us solve these problems, the equilibrium constant for water. Okay, if you've got water, okay, the concentration of hydrogen times the concentration of hydroxide in that solution will always be 1.00 times 10 to the negative 14. Okay, so we can use the water equilibrium to help us solve some problems. Okay, so let's say we want to figure out what the hydroxide concentration of a 0.05 molar nitric acid solution. We want to figure out the hydroxide concentration. Well, I know that my nitric acid is HNO3. Okay, I know this in my heart. Okay, so, and I know that my H plus is going to be equal to, my H plus concentration is going to be equal to the concentration of my nitric acid. So my H plus is 0.0500 molar. So my hydrogen times hydroxide is going to be equal to 1.00 times 10 to the negative 14 molar. Okay, so I'll plug in 0.0500 here, put that in the calculator. Negative 14. I just am actually having to type this in the calculator now, so I'm trying to find my negative sign. Here it is, negative 14 divided by 0.00. Nope, not 0.00. 0.05. This gives me 2.00 times 10 to the negative 13 molar is my hydroxide concentration. And you know what, guys? I'm thinking to myself, what if I wanted to figure out what the pH of this solution was? Well, the pH of this solution would be equal to the negative log of the concentration of my acid, which would be a negative log of 0.0500. Molar. So I have all these formulas that I can use, and I can really solve anything I want. Like I can solve using whatever equation. There's a lot of different ways that you can do this. Let's just get this. So let's do second log burger. Log. To type the number in first. So 0.05 log. That's going to get me 1.30. So that would be my pH. Okay. What is the hydroxide concentration of a 0.00128 molar sulfuric acid solution? All right, so we know that we're going to have to multiply this by 2 to get our hydrogen concentration. So our H plus concentration is going to be equal to 2 times 0.00128. So 2 times 0.00128. That gets me an H plus concentration of 0.00256. This line here is annoying me, so let me get my little thing here. Go away, thank you. Okay. So to solve for my hydroxide concentration, I know that hydrogen times hydroxide, OH minus, is equal to 1.00 times 10 to the negative 14 molar. I'm going to plug in this number 0.00256. Okay, and I'm going to do 1. I'm going to do 1 times 10 to the negative 14 divided by 0.00256. And that gets me a hydroxide concentration of 3.90 times 10 to the negative 12 molar. Oh, OH minus concentration. Okay. All right. So now we can do this from pH too. Okay. We can figure out the hydroxide concentration from pH. This sounds like fun. Let's do it. Okay. So we have a pH of 4.32. We can use the water equilibrium constant. I tend not to. I think it's easier just to do pH and pOH. So let's do it that way. So if we have a pH of 4.32, right, and I'm looking for the hydroxide concentration, okay, the hydroxide concentration, that means I'm going to need my pOH. So if my pH is 4.32, it doesn't really matter that a diprotic acid made this. My pOH would just be 14 minus 4.32. That gets me 9.68. Okay. And so if I want to get my hydroxide concentration, it would be 10 raised to the negative pH, 9.68. Turn my calculator over. Okay, so inverse log second. That's not right. Trying to figure this out on my iPhone, and that is not what I usually use for this. Log. That's not gonna work. I know what I need to do. Get rid of the second. 10. Got 9.68. Negative sign 10 to the x. That gets me 2.09 times 10 to the negative 10 molar. Okay. What is the hydrogen concentration of an aluminum hydroxide solution with a pOH of 3.89? So we're looking for hydrogen concentration. Okay. So hydrogen concentration given a pOH, I'm going to change this immediately to pH. Okay. So my pH, 14 minus 3.89. 3.89 gets me 10.11. Okay, so my pH is 10.11. My H plus concentration is going to be 10 raised to the negative pH. So I'll turn my cell phone around. We got negative. So our H plus concentration is going to be 7.76 times 10 to the negative 11 molar. What is the hydrogen concentration of a sulfuric acid solution? Whoa. Sulfuric acid solution with a very high pH. That doesn't sound good. pH of 12.29. Let me move this thing over. There we go. So that means my pH is 12.29. My pH equals 12.29. And if I have a sulfuric acid solution, that means when I get my hydrogen concentration from that, I'm going to have to then divide it by 2 to get the sulfuric acid concentration because it's diprotic. All right, so we're going to do 10 raised to the negative 12.29. Then I'm going to divide it by 2 because it's sulfuric acid. Okay, get my calculator out. So I've got 10 raised to the 12.29. So from 10 to the negative 12.29, I get 5.13 times 10 to the negative 13. I have to divide that by 2 because it's sulfuric acid, so I have to go backwards. So it's 1.70 times 10 to the negative 13 molar. Oh, and it looks like that's it. I'll post some other videos for you to look at too, but I wanted to make sure that I posted one of my own so that you guys could understand this, and I'll also give you some worksheets to work on. Okay? Stay well.